Good morning. Is this thing on? Yeah, it is. Okay. So my talk today is on payload development for nanosats. So these are small satellites in the few kilogram class. So we have a program here called CubeSat where we develop these small types of payloads to fly on a small spacecraft and hopefully do contributive science. And one of the payloads that's been in development for the past year or so is to study atmospheric gravity waves. Just the details of my talk. First, I'll go through, okay, what are atmospheric gravity waves? Why do we want to study them? Go over at the science objectives of some instrumentation that we would want to use, and then go through the mission implementation. What do we want to measure, and how do we want to measure it? And then the hardware implementation, the actual sensors, modeling them, and so on and so forth. And the signal simulation, how much signal are we going to get? What's the quality of the signal? And follow up with the instrument design overview. Actual hardware designs of instruments we have in mind. So atmospheric gravity waves, basically what are they? They are buoyancy waves that start in the lower atmosphere and then propagate up into the middle and upper atmosphere. They are generated in a couple ways. One is tropospheric winds moving over mountains start these upward welling buoyancy waves, and then they're brought back down, of course, by gravity. Another way is just the day-night cycling of the Earth's atmosphere. The atmosphere expands during the day and then contracts during the night and sends these pressure waves up and down through the middle and upper atmosphere. So one of the effects that very large atmospheric waves can cause is they go up into the ionosphere and can cause plasma instabilities. And these instabilities can affect and degrade communication and navigation signals. So there is an interest in getting a better understanding of these atmospheric gravity waves. And there are two ways to observe them. One is by a spacecraft platform. You see an image on the left, a mission, Atlas 1 mission, 92, looking downward at atmospheric gravity waves. I'm not sure the exact scale of here, but the scale of these waves is on tens to hundreds to 1,000 kilometers plus. On the right, we see an image taken from an all-sky imager in Colorado, so you're basically getting local information only. Whereas, of course, in a spacecraft, you can get global information about gravity waves. And these both have their advantages and disadvantages as well. So our science objectives for this instrument is to investigate gravity waves by remote sensing of the mesosphere. To observe gravity waves, we look in the air glows of molecular oxygen. As pressure waves move through the mesosphere, they excite the oxygen and cause basically brightness variations, and through which we can detect the gravity waves. We want to be able to provide a global measurement context for these waves to augment ground measurements that only get local information. For our observations, we want to be able to look at large amplitudes where brightness changes are at least 10% in magnitude. And large waves are of interest because they can propagate up into the ionosphere and cause these plasma instabilities. Also, through in situ observations or ground observations of ion density, we can get some insight into coupling with the ionosphere from these large waves. So for the specific measurements that we want to implement on this instrumentation, we want to look at the oxygen 00 band atmospheric emission and oxygen Hertzberg emission. The O2 atmospheric band is infrared. It's about 760 nanometers emission, where the Hertzberg is an ultraviolet from about 250 to in the 300 some nanometers. The brightness perturbation measurement in both of these bands provides for wave amplitudes. See how large the perturbations are. The ratio of the PNR branch of the O2 atmospheric emission gives us rotational temperatures and also wave amplitudes. And we can also look at phase between the brightness perturbations and the temperature perturbations in the wave. And this will give us vertical wavelengths. And if we have lastly, if we have a 2D imager, a camera, we can discern horizontal wavelengths. So this is a sample instrument which we developed for our ION 1 CubeSat spacecraft. This was developed at the university, which is our first CubeSat that we launched up back in 2006. Unfortunately, the launch failed and a bunch of CubeSats were lost, so we never did get any data. But this is the type of instrument on the left that we're going to develop. This is a photomultiplier tube, a very sensitive light instrument, basically. And on the right, you see that integrated into our CubeSat. And I have a little mock-up of, this is the size of a 2U CubeSat. And this is just a model, of course, but the bottom cube we usually relegate to the electronics instruments, and the rest of the spacecraft is for basically a payload. And we're currently designing a 3U, so it would be another 10 by 10 by 10 cube on top of this. So we would get basically a volume of this size for a payload, which isn't much, but you can do some interesting science with that size of payload. So for hardware implementation, like I said, for this instrument, we are looking at using photomultiplier tubes, specifically photon counting photomultiplier tubes. So they are extremely sensitive, and basically they sense individual photons striking the sensor. And they are excellent for looking at low brightness sources. So we have 4 PMTs at various channels for looking at the different oxygen emissions. Using narrowband filters. Also, we have, to get an idea of how much background there is in a signal, we look sort of off-band of the emission and look at a separate background channel to see how much noise we're getting. To measure the Hertzberg band, it's a wide, low brightness source. We use a broader bandpass filter. And these PMT measurements give us amplitudes and vertical wavelengths. We're also looking at a time delay integration CCD, a camera. And this will be looking again at the oxygen atmospheric emission, atmospheric band. And this will give us 2D structure of the waves. So this is showing basically the emission profile of the O2 atmospheric band. On the, these left and right features basically called the PNR branch. And we want to measure them individually. And the ratio between the two provides additional information on the waves. So these black dotted lines show the transmission profile that we have envisioned for our filters. And one engineering challenge of this is that these temperature profiles are temperature dependent. So the center band will shift to left and right based on the temperature of the filter itself. So we have to implement some, basically some little heaters to keep them at constant temperatures. So this is just this is a signal analysis for PMT channels. There are 4 of them. Just real quickly, the lens diameters on these are between 70 and 75 millimeters. So these are, I'll just show you. This is a 30 millimeter lens and filter. So these are pretty small scale, but sensor technology has gotten to the point where they're sensitive enough to be able to do these types of missions with small lenses. So that's good for us. Let's see, the footprint on the ground that we're looking at is about 12 kilometers. We'll be integrating and collecting signal about every 1.3 seconds. And the spacecraft moves about 10 kilometers in that time. So with that integration time, we can get a few points within, say 3 points within 30 kilometers distance, and that gives us enough points to look at, wave amplitudes on that length scale. Signal to noise for our is around 100 to 200, which will give us about 1% to 0.5% accuracy in measuring wave amplitudes. The TDI CCD is particularly attractive. If you're not familiar with how time delay integration CCDs work, most CCDs are frame-based, where you basically take a picture, you read out all the pixels. Time delay integration is for moving objects, where the charge on the CCD you can time shift in sync with an object that you're trying to image. So as a spacecraft flies overhead, we're basically moving the charge along the CCD in time step with the motion of the spacecraft. So we can get very long integration times, very good signal to noise for what we're trying to image. And for this particular CCD, looking at a footprint of 10 by 10 kilometers on the ground, we can get a signal to noise ratio of in excess of 500, so about 0.2% in signal accuracy. I think that's right. Let's see. This is a schematic of the one of the PMT channels. Fairly straightforward. On the right, you have the PMT sensor itself, which is just this guy. And on the left, you have an optics tube, an optical filter on the left, on the outside, and then an F1 lens. The CCD is a little more complex. Since the CCD has a wide field of view, and we need to filter that, we have to collimate the beam through this using a secondary lens so that the light transmitted to the filter is collimated. And then we re-image the what we're looking at on the CCD with a third lens. Let's see. Anyway, this is a picture, but I guess I don't need to show this. This is basically a picture of a test PMT that we've been working with in the lab, and this is the actual PMT that we, or the model that we would look to fly on the spacecraft. And you can see through this is a pretty small-scale instrument. And going back to our CubeSat, so we have a volume of about this size. We can fit about 4 of these. 3 or 4 of these packed into a payload size of this, or payload envelope of that size. So there are 2 spacecraft platforms that we are looking at to launch up this instrumentation. First, again, our CubeSat program here at Illinois has been developing payloads and spacecraft since about 2001. Our latest CubeSat is called IlliniSat, which is basically the bus, all the electronics that'll run the spacecraft. And separately, we're developing payloads for that spacecraft, and we can get about 2 to 3 kilograms payload for this platform. And it's capable of supporting 3 to 4 channels of PMT instruments, but unfortunately not the CCT is just not capable enough, and it's not enough size. And in the current development progress that we have, our CubeSat developed on campus will be launch capable in the next couple of years. Another one that proposal is just going into NASA. We're looking at flying a student experiment on an Explorer class mission. So this is a major NASA spacecraft proposal, and of which the student experiment would be a small part, but we would get to fly, if awarded, on a NASA spacecraft and do some interesting science. We proposed a 4-channel PMT to fly on this spacecraft, and hopefully that we're developing the TDI CCD instrument in hopes that we can add that on as well if we're awarded. This gives looking at the ICON student experiment. ICON is the mission being proposed. on the right, we see basically a solid model of how it would look. It's similarly sized to a CubeSat. Dimensions are a little different. But again, this just shows the kind of the mass breakdown, sensors, electronics boards, and structure and wiring and so forth. It gives us a total mass of about 2.4 kilograms, so a very light spacecraft instrument. Just going over quickly the power and data requirements for this instrument on the spacecraft. The spacecraft itself would be providing our power and communications and attitude control and all that. So all that the student experiment needs to do is basically gather data and give it to the spacecraft. So our power breakdown is, of course, we have to run the sensors. We're running them only at night because that's when the best data can be taken. During the day, there's just a lot of noise. We're running 2 heaters to control the transmission profile of the 2 narrowband filters, and basically we have our command and data handling electronics boards. All total, that gives us a power load of about 1.8 watts. And with a DC efficiency of about 80%, we have about 2.25 watts total average power. So this is a very, very low power system, as all spacecraft payloads need to be, of course. So that's it's pretty amazing that we can do good science with that little amount of power. Data rates is pretty low, about 2 megabits per day from the PMT instruments, and for about a year or 2 mission, that the total amount of data that is produced by the mission you could easily fit on a flash drive. But it is definitely interesting science that we can do. If we fly the CCD, data rates go up by the factor of probably 100, just because of the 2D information provided. But that hasn't been approved yet. So anyway, I don't know how long I took, but that was my presentation. Any questions from the gallery? Hey, thank you.